doing the same thing. It was like cycling the charging, flashing on and off. How can the charging circuitry have gotten this destroyed? This is catastrophic damage of the charging circuitry from one bad charging event. I've never seen anything like this. Hello, this is Aaron with iBoard Repair. Today I'll be diagnosing and recovering data from this iPhone 16 Pro Max that died on my customer after he plugged it into his charger. He reported that it got hot and would no longer turn on. I don't know anything about this device other than what the intake form has told me, so let's get started diagnosing it. I have my motherboard here. It's out of the housing. Before I took it out of the housing, I tested with my USB ammeter whether or not the phone was charging. It's not charging, doesn't take any amperage. And when I'm working with the phone, that looks like it's not turning on or charging. My first step is to take my DC power supply probes and touch them to the battery connector here and see what happens. And the first thing I look at is my DC power supply is giving me an amperage draw before I told this phone to turn on, so it shouldn't be pulling anything yet. This should be flat 0. Let's see if it changes, if it turns on, or if it looks like it's short when I actually prompt it to boot. So I'm going to short the power button line right now. That doesn't look too bad. That looks like, let's see if it's going to move forward. It looks like it's booting. So this does appear to genuinely be a no charging case, and that phone couldn't turn on simply because it can't take a charge. So what I should do now is give this motherboard good parts and see if it actually turns on and whether or not it will take amperage and whether or not it will connect to a computer. So let's check that out. I've got the parts connected here. Let's plug in the charger. So it doesn't appear to turn it on, and it doesn't appear to be taking any amperage through the charge port according to the ammeter. Let's short the power button and see if it actually will turn on still through a power button prompt. I did think that might be the case. Oh wow, it actually booted. So it did boot loop like 3 times before it actually turned on. I didn't expect it was going to turn on, and I'm almost sure it's not going to connect to a PC still. But let's just see. Either way, I mean, it doesn't matter. We're over here on 1%. This battery is not 1%, so this has a charging IC problem. It's not able to read the battery data. It's not able to prompt to boot. The charging chip is surely bad. So I think now's a good time to look at the 4 charging chips and how they relate to charging the phone on these newer model iPhones. I've recently had a video where this chip went bad and it had some specific signs. And these 3 chips right here are the main charging ICs. These 2 are actually the main charging ICs. This is the main charging logic, and this is paired to this ROM over here. Let's kind of diagnose these, or let's kind of dive into these. To start with, we can start at the charging port FPC. VBUS1 E85. This is the voltage from the charger. It goes both into the charging IC here, as well as into this MOSFET here. On the other side of this MOSFET, it goes into the charging logic chip. So again, starting from the charging port FPC, that voltage is going to go into U4000 here. U4000 shows the VBUS as an input here, and it's going to spit out PP, VDD, SNS, BPIC. And where does that go? That goes over to the second half of this charging pair. If we look at the schematics for this chip, we can see its inputs are PP BAT, VCC, BPIC, as well as PP VDD, SNS, BPIC. And this VDD, SNS, BPIC, that's the output of the U4000 here. Same output right here is the input. Same line. This line, or this chip, is actually the chip that will produce VDD main. So this is like it's taking both power from the battery here, power from the charging port. It's mixing them together, and we're getting our VDD main line, our main line that powers the entire phone. It is important to see that U4000 here, it doesn't spit out main. It doesn't take the charging voltage and spit out main. It spits out this intermediary line, VDD SNS BPIC, which is the input for U4200 that then spits out VDD main. And if we relate this back to what I have here, we have a 0.06 amperage draw on my DC power supply before prompt to boot. We have a phone that will turn on when I prompt it to boot. It will fully power on. So PMIC is turning on and staying on. It's not spiking up and then turning off. And it's not staying a high amperage draw, because we have to think about the power lines that can cause that type of amperage draw. So if we look at some of the power lines on U4000, its main input is the charger. It has a few other lines here, like PP charger, LDO internal, PP charger, VDDP. We can see PP charger, VDDP is at H7, corresponding to underneath this pad. H7 would be VDD main. And I've seen a short on a very recent video that I've made on another 16 Pro Max where PP charger, LDO internal, it was short at this capacitor here. And when I tested the amperage draw before prompt to boot on this phone, it gave me a 0.8 amperage draw right off the bat, steady, kind of like a main short, but a main short would give me a maxed out amperage draw. This gave me almost maxed out, but it was limited to 0.8. And I actually have a case study for that. I could show you that right here. I'll go over to my website. Case studies, dead, no power. 16 Pro Max, no power, data recovery. I did a recent video on this one. I've made a case study on my website, but if we look here, the board immediately pulled a 0.8 current draw before I even tried to boot it. And it ended up being a short on PP charger LDO here. So I have previous evidence of what it looks like when one of the power rails are short on this chip. And that 0.8 doesn't look anything like our 0.06. That's not to say that one of these other power rails wouldn't show something small, but these power rails are kind of more critical. If this was short, we would see like a mainline type short. If we look at this chip, its power rails are even, more critical. It's our battery and our charging line power. And when this goes short, it acts just like a VDD main short. So if a short on its input here, VDD, SNS, BBIC, if one of these caps goes short over here, it will look exactly as if a mainline cap went short. There's no difference on the amperage draw. And that's because this is connected directly to VDD main as an output through this chip. So U4200 would look like a full main short. U4000 looks like a secondary power rail short, so it looks more severe. For another example, PMIC outputs have different levels of shorts. If it's a buck converter, one of these power rails goes short, we'll usually see like a high steady amperage draw. It can be like, 0.8 steady. It just stays very high up. Similar to how this chip was, it could be, if RAM was short, it would be something like that, just some high amperage draw, not fully maxed out, but quite high. It also has LDOs. So LDOs would be something like these NAND lines. It doesn't go through one of these coils. And these lines are still split further into two categories between critical and non-critical. And this is a critical NAND line. If this line is short, the PMIC will automatically shut off and it won't continue to try to boot. So that's when you'll see like a high amperage draw spike that falls back down to zero quickly, as opposed to like a steady high amperage draw that you might see on a CPU or RAM short. Having said all this, there's still another type of LDO, and that's a non-critical LDO, and that could be other lines that won't necessarily shut off the PMIC if they're short, but they're still going to affect it. And I think that's what we're seeing with our 0.06 amperage draw. It's a non-critical secondary line that's short. So it could be something like, let me see, like an audio line, audio power rail. Another example of that would be if we look at our U9500 here, which is our charging logic IC, we can see that the charging voltage does come here as well, but it has this RVP tag, which is what it gets when it comes on the other side of this MOSFET here. So this is the charging voltage, and it turns into this line that has that RVP tag at the end of it. And that RVP stands for reverse voltage protection, I believe. So it goes through that MOSFET, it gets a protected voltage here. So this is a more protected chip. It doesn't have a more direct line to VDD main like something like U4200 would. So that definitely wouldn't give me the full main-like type amperage draw when one of its power rails goes short. But that's not like its main power. It just it's sensing that you plugged in a charger here. Its main power comes from these lines here, and these are outputs of the PMIC, and these would be like more of the non-critical secondary LDO power rails that I was talking about. If one of these were short, it doesn't seem super critical to prevent boot. Maybe this one actually is, but these other two are not potentially. This one is, this one may not be, this one is, this one may not be. So 3v3 and 1v8 I can see as being measurably short right now, but we can still go one step further because what this chip is producing is this PP3v3 LDO E85, and that's going to take us over to our ROM here. That's the input here. PP3VO LDO E85, and this is a power rail that was created by the charging logic IC, which isn't as nearly as secure as something like the PMIC. It doesn't have nearly as many checks and it's not as complicated. So this line is a good example of a secondary non-critical power rail. It's only produced by this otherwise protected charging logic IC. And I think this is the line I want to measure first. And I want to see if we can just pinpoint what line is short before I do anything else, before I split the board, before I take any measurements. I want to bet that right here, this output is my shorted rail. I should be able to measure that right here. So that would be nice to see. If it's not that, I think I would like to measure the inputs for this chip instead and check PP3v3S2 and PP1v8S4. So let's just go ahead and take another look at the motherboard and measure those three lines. I think we can find all of them on the top, right here, right next to it, and right above it. So we just need to pull up this shield, reveal these chips, and I can take measurements here. And it would be nice to find a short. There shouldn't be an amperage draw before prompt to boot unless there's a line short. So we don't need to blindly replace chips. We can find the line that's short. And you guys should keep in mind that these are just my interpretations of these lines. I don't necessarily know for sure that this is exactly how it works. I'm just presenting what I think makes the most sense. And to sum all of that up, basically U4000 gets voltage from the charger. It turns it into VDD, SNS, BPIC. BPIC specifically, I think, stands for battery power IC, which is the U4200 chip that turns the battery power voltage along with the charging voltage into VDD main. So U4000 produces that power rail that U4200 uses to turn into VDD main. U9500 is the logic IC. It knows what's plugged in, whether that's a charger, whether it's plugged into a computer, whether it's an accessory, along with probably other things. And the ROM is paired to U9500. So that's about how it works. There's probably a whole lot that I'm missing, but that's how I understand it in my own head for the most part. Those three chips are going to be right here. So let's pull up this shield, get access to those capacitors and measure them. You have to be very careful if you remove shields with this method that I'm using here with wire cutters. I usually start on this corner where I know I'm not going to damage anything. This corner has a small potential to damage a little cap. That doesn't really matter too much, but this is where I'll usually go next. Looks like I hit a couple of caps, but those are not too hard to fix, and I believe they're not even critical. And I do need new wire cutters. I have a gap now. This one didn't used to have that, but this is my last set I have for now. Important not to damage that chip. There's, I think, a capacitor. I don't think there's much right here. Pull that up. And then these two spots are where you have to be most careful. And then this last corner, you can kind of just wiggle it off and apply outwards pressure only. So all these power rails that I suspect are exposed. Let's see if I'm smart or if I'm way off. I don't really know if we'll find it. So I'll turn on my multimeter and I'll check that line that I suspected most first. PP3B3 LDO E85. That is right here. Let's see if I'm a genius. I'm not a genius. We can check some of these others. So I think next, I just want to see where the heat from that 0.06 amp draw is actually pointing towards. I want to make sure it's pointing to this chip. It could also be pointing towards the ROM, which we wouldn't be able to see here, but let's just see what we get. So I'm going to set my DC power supply to my battery voltage. I'll inject voltage into, oh, I cannot inject into the battery connector. I'll inject directly into main in this case because the battery connector is on the opposite side of the board. Okay, something interesting. I have a couple of test points right here. This one is VDD main. This one is VDD SNS BPIC, which is the output of this chip and the input of this chip before it turns into VDD main. And both of them are supposed to be near battery voltage. And if we look at my DC power supply, when I inject into VDD main on this side, DC power supply shows 0.02. When I connect into VDD SNS BPIC on this side, we get that full 0.06 that we saw, same as if we go through the battery FPC as opposed to VDD main. If I take my thermal cam here, so if I try to inject into VDD main first, not seeing much on the thermal cam and only that 0.02 amp draw. If I move it over to VDD SNS BPIC, we can see something heat up. You can pretty clearly see it's the middle chip. So it was clearly this chip heating up. These were the 2 points I was injecting into. It says resistor, but there's no resistor here. It's just the pads. This one is the BAT VCC BPIC. So I thought this was the VDD SNS BPIC. I thought it was that one. It's actually PP bat. Okay, so that's just the battery connector. So that was working as the battery connector. This was working as VDD main. So this is the same as when I was injecting into over here, same line. Let's take a look at some of these lines again and see which one may possibly be short within it. So I was going ahead and measuring some of these lines attached to U4000 and turned out to be this one, CX C-Fly N1 charger, which is the other side of the CX C-Fly P1 charger, P for positive and for negative. And I do believe this is some sort of power system for the chip internally, but I'm not 100% sure. But at least I do believe this is like a very secondary power rail, a sub-secondary power rail that got short, which is why it could be classified as non-essential and allowed the phone to turn on even though this line was short. And it's surely short through the chip. This isn't like a capacitor or anything. This doesn't attach to ground anywhere. You know, this is the line here. It's the negative side of this little system here, which here's the positive side. There's two bigger caps over here. Here's the negative side attached to these little caps and into the chip again. And I've seen this spot short before on a different video. And now I'm seeing this line short. And it's making me think that the power surge just kind of starts at this side of a chip. If you plug your phone into a bad charger, a bridge occurs here and it blows a little microscopic hole and permanent fuse to ground. So let's pull this chip off, make sure the line clears, and then as long as we can measure it clear, then we know we can go ahead and just replace the chip and we're good to go. Let me show you the measurable short before I do that. So that was this tiny little cap right here. In order to even measure it, I have to use my tweezers as a probe. So I'll grab my probe with tweezers and use the tweezer point as my new probe. So red on ground, the black on this line, and we're getting that 0.008. The positive side should still be something normal. 0.5, that's normal. This is not normal. And it's also no point in taking this capacitor off. That capacitor has no pathway to ground. It is not the problem. It's definitely the chip. So let's just go ahead and remove this chip again. And how funny, this chip could be responsible for the phone not turning on, as like one of my last videos that I had on an iPhone 16 Pro Max. Or this chip can be the cause of no charging, but the phone does still turn on if you give it a good battery. So a lot of different behaviors I'm seeing on this iPhone 16 Pro Max in regards to these charging ICs here. Time to finally just get this finished, and very luckily, I shouldn't have to split this board. This phone should still be usable. I just need to replace this chip. I don't usually have a SIM tray on this model, so this is an international model, I believe. So I have to approach it from this side in this case. I had really assumed that this chip would have been the problem. And that's why it's really important to diagnose properly and not just replace chips blindly. It's important not to guess and to have a reason for doing the things that you do on these motherboards, because that would have required me to split this board and change the paired chip as well. And that would have caused so much more work than just removing this chip alone. I don't see really any physical indications of a short. So now let's just go ahead and measure that cap again and see if it's no longer measuring short. And there we go. Oh well, that's what it should be measuring. If I reverse polarity, it should still be OL, I think. Yeah, and if I reverse polarity while the chip is on, I should get a reading. Because if you remember, when I measured this side of this capacitor, I had a reading before. Now I will not. It's because the chip is gone. So, easy. Very simple job. I'm very glad I don't have to split this interposer here. Split the sandwich. Unfortunately, I do not have a new chip, so I'll have to harvest it from this extremely messed up board, but that's fine. I'll pull it off of this board and then I'll reball it. And we'll put it onto our client's board here. And then this phone should be perfectly working again, allowing him access to his data, but also allowing this phone to fully function again, just as a bonus in this case. So I pulled the charging IC off of the donor board. I've added flux and I'm going to go ahead and flatten the pads underneath it now. And now that my chip looks clean, I can go ahead and use my 16 Pro Max reballing stencil here. I like to put my solder paste onto a paper towel and give it a very quick blast of air. Dry it out just a bit. Pat it dry as it's still a little bit wet, and that'll give you a pretty good consistency to work with. So I'll go ahead and spread the solder paste onto the stencil now. And I'll apply some heat. I use about 280 when I'm reballing. That looks really good and ready for use. Let's get ready to put the chip down. I like to give the board a little bit of heat first, and that will allow the board to get a little warm. So when I put down flux, like now, flux will melt a little bit easier, and it won't need to melt again once I put the chip down and pull the chip out of place. One last check before this chip goes down. Let's make sure that that amperage draw from earlier actually did go away. So I'll apply voltage to VDD main. I'll apply to bat VCC. I'm getting a small draw, but I'm not worried about it. 0.01. So I'll go ahead and apply hot air now and attach this chip to the board. And there we go. It looks like it moved into place. Okay, it looks pretty good. Let's go ahead and first test that capacitor. Make sure it's not short again. 0.41. 0.41, huh? It's a negative line, so I don't feel like I should have that reading there. Well, let's prompt it to boot first and see what it does. That looks normal, but I'm still concerned about this amp draw before prompt to boot, this 0.01. Not sure what's causing that at this point. So let's put this board in the housing and see if it's turning on and charging normally. So I've done my first test, and it does turn on, as you can see, and it does read battery data, 96% here. What it doesn't do is recognize the charge port very well. It turned the screen on, but it's like flashing on and off here. And it's not charging on the ammeter at all. It spiked a couple of times is all. That only leaves a couple options in my mind. Hopefully the charging port itself went bad, and that's the simplest solution. So let's try a new one first. Take this back out of here, and I'm going to test with only known good parts instead. So I have a good charging port connected now. Let's see if we have any difference. Wow. Still no amperage draw. I think we have a problem with both of those chips. I mean, all of the chips. That's crazy. Let's see if it will connect to a PC in the state that it's in. No, it tried to connect to a PC and then it's powering off again. Okay, this got way more interesting and confusing. I could not really get over the fact that I still had this amperage draw when I connected to either main, like this, 0.015, or even to bat, 0.015. And it leads me to believe something else is still wrong. So that line was short at that capacitor. It wasn't short at the capacitor, but that capacitor indicated that the line was short. We saw that it cleared. That line is good. Well, that line is a negative line. And a negative line should not give me a diode motor reading when I'm measuring positively, only when I flip the polarity. Is my chip still bad? Here's another donor board. I'm gonna have to crack it open and just verify that line. I'm almost positive that I should have no positive diode motor reading on that capacitor. And I want to make sure on this good board that I don't. 0.4, never mind. That line's fine. I'm glad I checked it. So I'm gonna check heat again. Maybe I'll have a different heat signature now that that first short is clear. And it will go towards this this lesser short that's still on the board. I can't see any heat. Let's try to inject into the bat line now. Well, I was hoping to avoid splitting the board, but it looks like that's not going to be possible. I'll have to split these layers apart to get to the inner components and take a look at that and see if any lines associated with the ROM for this chip are bad and if we can identify those and fix them. And I kind of suspect now that this chip may have also gone bad, or the ROM associated with it. This chip is much less likely in my opinion. This just shows that my guesses and diagnosis from earlier are just that. They're just me guessing and trying to make sense of what I have in front of me. But it's always just a starting point, and I have to work with what I actually measure and find on the board. It is very interesting that that was a measurable problem that was fixed when I replaced the chip. So that was a bad chip. So it's always smart to take a step back and think about the problem. And I just did that. I thought about when this chip was bad, we had a 0.06 amperage leak on the BAT VCC line, which was right here. But on VDD main, we only saw that 0.02, which is still here. And at that time, I assumed it was the same issue and it was just showing differently on VDD main. I'm now thinking this 0.016 that we have now was that original 0.02 that's still here showing on VDD main. When it was 0.06, it didn't show on VDD main. It only showed on BAT VCC. And that's because the problem occurred at U4000. And U4000 isn't attached to main. It hasn't made it to VDD main yet. So the 0.06 leak was showing only on the BAT line, not on VDD main itself. In the case we're at right now, I still have a 0.01 amperage leak. And this side is BAT VCC. We can see that 0.016. In this case, we also have the 0.016 on VDD main. And if I have an amp draw before prompt to boot, it has to be leaking from a system that is either after this stage and also directly connected to VDD main. U9500 isn't connected to any VDD main. It's not connected to VDD BAT. It gets its power from the PMIC, and the PMIC does not turn on just by touching voltage to main or to BAT. It needs to be prompted to boot in order to turn those power rails on. So if there was a short on a line connected to this chip, I don't think it's possible for it to show before prompt to boot. I think it would have to show after I prompt the phone to boot. And I was thinking about all of this. Hopefully that makes sense and I kind of got that idea right. But I was thinking about this and it made me check, if it's an amp draw before prompt to boot, it had to have made it to VDD main if I'm getting the amp draw on VDD main. So the short had to have made it there. So I started checking the capacitors on this line. And this capacitor has one line on the chip and it's good, one line on ground. This capacitor is supposed to be a positive and negative in the same exact way that this one was. And this one showed us which line was short under here. It was the positive end of that little power sequence, whatever it is. This capacitor works in the exact same way. I have a positive side and I have a negative side. And this side is short and it shouldn't have any pathway to ground. Let me show you on the schematics what this one is. The second capacitor here on this side of it. So I measured this capacitor first and we saw this was good, this was ground, and then this was ground. It's the VREF Filt negative BPIC. This one is VREF Filt positive BPIC. In the same way that this other capacitor that showed this line bad, this was the CFLYN line that was bad, and this was the CFLYP line on the other side of the capacitor. And this side was short to ground with no pathway to ground anywhere. Same thing with this line right here. We just measured that this one is short. It also has no pathway to ground anywhere. So that power surge blew a 0.06 leak into this chip. It allowed enough power into this chip to blow a 0.01 leak into this chip. And because there's no pathway to ground, it again tells me that this chip is bad. So this should fix it finally once I replace this chip. I'm very glad I thought about that instead of blindly splitting this board or removing this chip without having any reason. The 0.01 leak, it told me something had to be short. It was a good idea to find what that was before we did any more work. So one more time, it's this little line right here is measuring short. I'm going to remove this chip and then we can check that line again and see if it clears. And then we can also check to see if our leak clears after that. I hope I made that make sense. It's kind of hard to make sense of it in my own mind still. I have a loose grasp of the charging sequence and logic. It's pretty complicated, but I'm glad I decided to think about it a little bit. Let's go ahead and just remove this chip and hopefully this will finish off this job. So I'll put some flux down and then we can use our hot air to remove the chip. I usually use about 370 on my hot air. The chip is removed, so I'll just put a little bit more flux and I'll go ahead and flatten these pads while the board is still a little bit hot because it's easier to do so when it's like that. And then I'll go ahead and check that capacitor to make sure it cleared. Now I can see if that capacitor has cleared. Great, we can see it's no longer short. And now I should definitely check to see if I have any type of leak left on either main or bat, which I don't think I will anymore. Let's check bat first. No leak. Let's check main. So this is crazy. How okay, so no leak on bat. That's fine. This was the chip that connects main to bat. With it gone, then it doesn't have that downstream effect. I still have a leak on main. If I still have a leak on main, the same leak, that means once this chip is placed back down, I will still have a leak on bat as well. But it tells us it's on the main side for sure. And also, this is another separate problem. This was measuring short to ground. Once I put this chip back, this will still be clear. It won't be short to ground. And this will still be 0.016, and this side will also be 0.016. So the 0.016 wasn't even related to this other problem that was causing my bad charging, I'm still assuming. I still have another different issue here that it may or may not matter. Okay. If it can charge normally, if it can connect to a computer and it has a 0.016 leak, I don't care. The reason I was tracking that down so hard was because I still don't have a working charging circuit here. I still was not able to connect to a PC and I still was not able to charge the phone. So I think I just want to put this chip back and then I want to see if it will connect to a PC and if it will charge. And if it does that, then that's probably good enough for me to take data from it, even if it still has that 0.016 leak. I can try to track down what this 0.016 leak is, but it's not necessarily related to any of the charging. It could just be some other, what could it be? A leak on main somehow, which can be caused by like a lot of things. I had it all connected because the phone's not charging, making me assume it's all one issue. But this is already one issue. This is issue number two. They've both been proven and cleared, and the 0.016 is another issue. And that's kind of crazy that like one charging incident caused all of this damage. I'll go ahead and take this chip now and reball this. And let's just see if it fixes the charging issue, because this is a data recovery job and I just need to find a way to get the data. As it is now, the phone does turn on, but I doubt it would be able to, it wasn't able to connect to a computer, but I'm wondering if I would have been able to connect to Wi-Fi still and have taken data despite having this issue. It doesn't matter. Let's go ahead and just replace this and see what we can do after that. I'll go ahead and apply my soldering paste to my stencil again and reball this, what is this, U4200 chip? The chip is ready, so let's go ahead and just place it onto the board now and get this finished up. I do still have that leak, but I think it's not going to matter once this chip is replaced. I think I'll still be able to pull data from it either way. Step one, let's go ahead and see if this line is clear still, if it remains clear. No, it goes back to short. What is this? All right, check a donor again. I need to make sure. I've been proven wrong time after time after time on this case so far. Oh, that's annoying. That line is normal, and the schematics are wrong. Which can happen. They're not always right. Let's take a look. Clearly, I was measuring here. Clearly, this thinks it's right here. Whatever this is. I don't know how to interpret that. Other than that, it seems to be incorrect to me. Maybe it's saying that there's ground in the chip on these lines or something. I don't really think so. I'm just seeing that it's wrong on both of these fronts. And anyways, it cleared when the chip was off. I don't really know what that means, to tell you the truth. Maybe that's just ground on the chip at D1. Let's just go ahead and check how far the charging voltage is getting here. So I've just gone ahead and plugged in my USB to give it USB power. And let's see where this voltage is going. Do I have USB power anywhere? I should at least have it on the USB power line directly connected to it, which is right here. We got that 4.9 up there on my ammeter, or I'm sorry, on my multimeter, which I have in voltage mode now. Um, so that 5 volts goes through U4000 here, and it turns into VDD, SNS, BPIC, and that feeds this chip, which is over here. Let's see if the charge is getting through to here. We do have 4.4 there, so that is doing its job of turning the battery, I'm sorry, the charging power into this line here. So the power is being delivered through this chip properly. This chip is turning power into VDD main properly. Where do I have VDD main? I have VDD main right here. We've been using it. And I got my 4.4 up there. So this chip is doing its job as well. And process of elimination. I don't know why I have a short or a leak on my main line, but now I think that's going to be a third unrelated problem. And I have a no charging issue. My ammeter, despite turning on these power rails over here, my ammeter still reads 0. It's not pulling anything from the charge port. I'm not sure how that works when I have 5 volts there, but that's what it's reading. But I have to assume that leak is a separate issue, and by process of elimination, I still only have my logic charging, my charging logic IC now. And that's probably the reason why it's not charging. It's really the only reason left. I mean, there are more obscure reasons, but this is the most likely reason left. U4000, the charging IC, had a definite measurable problem at that capacitor that was giving me a reading close to ground when it should have been 0.5 or something like that. And we saw that line clear when I pulled the chip, and it stayed cleared when I put it back. I thought I found a similar line on U4200 here because the schematics show it as a very similar looking sequence or line. It showed it as a positive and negative on one side of a capacitor, and in this case, the negative side of this capacitor appears to just be ground, but it's only there when the chip is down. When I pulled the chip, the ground line disappeared from the capacitor. It turned into OL. When I put the chip back, that ground line came back. And to be sure, I measured on a donor board that's perfectly working. And on that board, that capacitor measures ground in the same spot. So that tells me that should be ground. It's a normal reading, and either I'm misinterpreting the schematics or the schematics are wrong. So U4000, it was smart to change. U4200, I think it was reasonable to change, even though it ultimately ended up being a false diagnosis. And that only leads me to U9500 that I have left. I'll change that. And unfortunately, it is paired to a ROM, so I will have to split this board and replace both of those chips. And if you ever have an iPhone that's not charging, replacing all of the chips is a way to do it. It's not the best way, but it is a way. In this case, I didn't have much of a choice. I had definitely at least two problems because, as I keep saying, this one had a problem. It was fixed by changing it, and it has another problem. And apparently it has a third problem, a leak that's unrelated to the second charging problem. Sorry if that's confusing. Sometimes board work is confusing. The top board is the RF board, and there's no reason really not to heat it early. There are a few underfilled chips, but only like one or two, maybe even just one. And for data recovery purposes, it doesn't matter at all if this top board is overheated. So it's just smart to heat it from the top. The very first thing I'll do is check to see if my leak is still here. I guess I would like to see if I inject into main, if I can see anything heating up on this inner side when I use my thermal cam. I'll do that real quick off camera. If I find something, I'll let you know. I'm a little confused about what I saw in that thermal cam. It almost looks like this is heating up at this chip, but I couldn't quite tell. Accessory, this is something to do with charging. It does connect to main as well. Let's check if any of these lines are short. Not short. No way. Let me show you what that capacitor is. By the way, I don't know if you guys have noticed, but my voice is a little rough on this video. I'm getting over a sickness, and I've been getting over losing my voice as well. It's barely come back. Anyways, this line right here is what I just measured, this capacitor. This is some line that connects to this chip here. What is this chip here? I haven't really looked at it before. I don't know what this is. I just know it ends with a accessory line, PP5 V25 ACC, something to do with, oh, I know what this is. This also proves that I wouldn't, okay. This chip is for accessories. So for example, sometimes I use a USB-C to Ethernet adapter in order to give Wi-Fi to devices that otherwise wouldn't have it. And if this chip is not on the board, then that component, that tool will not work because it plugs in through the USB. So that's a USB accessory. It's something other than the charger. And this is the enable line for that. And the enable line appears to be short, fully short to ground. This is a 39K resistor, so we don't have to worry about checking the other side of that. It's either this capacitor or this IC is short to ground. 3v3. So I should at least be able to give 1 volt to the enable line here. Yeah, 3v3 is on the other side of the resistor here. I'm sure it's probably close to the same. I'm just going to use 1 volt and it's probably fine. And I want to see if this capacitor or the chip heats up under the thermal cam. Kind of hard to see it, but it only looks like where my tip is touching is actually getting hot. Also, if you didn't notice, that enable line was taking like 0.8 amps or something like that, so it's definitely abnormal. This isn't a case of a false like interpretation of the line or a wrong schematic. I'm just going to take this cap off first because there's a good chance it's just a cap according to the thermal cam. Looks like it broke. That's also a good sign that it was bad. Still short, so let's go ahead and remove the chip. Let's see if the line has cleared now. And the good thing about this chip, it's not actually needed to boot the phone or for me to pull data. It's needed for accessories But in this case, I have a working RF board. It doesn't even matter if stolen device protection is on this device and I can't plug it into a PC. I can still use the RF board to connect to Wi-Fi. So the line's no longer short. And I think our amperage leak may be taken care of. Maybe if we're lucky. I've been wrong a lot in this video, so let's see if I am again. Do I still have an amperage leak on main and bat? No leak on bat. No leak on main. So a little bit ago, I thought it was going to be U9500, and I thought that the leak was not connected to the charging circuit problem, and I've since proven that is incorrect. This leak was connected to another charging IC, a much smaller one that has to do with the USB accessories. And the USB accessory enable line was short to ground, and it was pulling 0.8 amps if I touched it with a 1 volt probe. So it was pulling as much amperage as it could. I removed the capacitor first to make sure that wasn't the short. It wasn't. I removed the IC itself. The short cleared. The leak cleared. My charging problem probably cleared. And this phone will probably turn on now. And I should check to see if there's stolen device protection. And if there is stolen device protection, I need to put it into a jig and see if it can still connect to Wi-Fi within the jig, which I believe it can. The Wi-Fi chip's on this board. So I don't think I have any real reason to need that chip on the board at this moment. Let's go ahead and see if it will actually charge when connected to a charger now. Now that the board's been separated, I will have to put it into a testing jig, but let's go ahead and do that and see if we're actually getting normal charging at this point. And before I test it, it actually ties back to something I said earlier. I said I shouldn't see an amperage draw before prompt to boot unless it's through an IC that connects to VDD main. And this is an enable line that goes through this chip, and this chip, its main input is VDD main. So it does directly connect to VDD main, showing that statement, I guess, is probably still true. I'm glad to see that it does connect in some way, and that makes it make sense to me. I've got all the parts hooked up. Let's see if it wants to charge normally. No prompt to boot from charger still. Let's short it. How can every single circuit be damaged here? How many problems on these charging circuits can I find wrong and still have no charging? This is getting ridiculous. Doing the same thing was like cycling the charging, flashing on and off. My USB ammeter will occasionally flash a reading, but usually 0. How can the charging circuitry have gotten this destroyed from one event? That's the most catastrophic damage I've ever seen. Most people use the word catastrophic damage very loosely when it comes to repair. This is catastrophic damage of the charging circuitry from one bad charging event. I've never seen anything like this. How frustrating. We cleared a few issues now. We cleared the no battery data and bad reading on this capacitor by changing this U4000 chip. We cleared a shorted enable line on the U9800 chip, which cleared the 0.016 amperage draw we were seeing on main and VBAT. I now have a phone that won't charge, but the charging icon flashes on the screen. And again, process of elimination, we're getting real close and down to it. We have U9500, which can definitely be causing it at this point. But, you know, U9500, one of its inputs is a charging line, but it's a RVP, reverse voltage protection version of that charging line. So here's the VBUS. It blasted a hole into U4000 here. It goes through this MOSFET, spits out the VBUS RVP line before it goes into U9500. So if this is not working correctly, it could be the reason why it's giving us that flashing charging icon. Maybe it thinks it's working and then it realizes it's not, and it shuts it down. So I was going to test this. It's pretty easy. We can just plug the charge port in and see if it's going to spit out the VBUS RVP line right here at this component here. This is not actually accessible, it's covered, but we could have checked it here or here. But now I've already split the board and it's in a testing jig, and this part of the board is completely covered, so I can't do any testing on these components anymore. So I'd like to test this MOSFET, but I don't really have an easy way to, so I'm just going to replace it just to see. It's easier than replacing this chip and the paired ROM first. I can just go ahead and replace this and just see if maybe that solves the problem, just because it is a possibility. I don't know that it is the cause, but we can check pretty quickly. Let's do that next. Kind of at a difficult spot, but I should still be able to get into there. And I'll go ahead and harvest the MOSFET from a donor board now that I've removed it from the client's board. So I'll just go ahead and test that, and we can just make sure that that is not the issue before I move on to U9500, the charging logic IC. I checked really quickly with just the charging port and battery plugged in, and I was getting no amperage draw, so still no fix from the MOSFET. Let's go ahead and finally change the charging logic IC along with the parity prom. I've pulled the chip and I'll clean it up while the board's a little hot still. It makes the solder come off of the pads a little bit easier. Add a little bit more flux down. This donor board has certainly came in handy for this repair. I've applied solder paste to the stencil. Let's go ahead and reball the chip. And the ROM is the last thing I need to change here. So I'll remove the one that was paired to the damaged U9500. And now I'll harvest the donor ROM from the same board that I harvested the donor charging logic IC, U9500. Surely this is now fixed, right? Surely this is fixed. I'll clean it up, I'll put it into the testing jig, and let's take what I can only hope is the final look at this. Okay, moment of truth. Let's see if it turns on. If it prompts to boot through the charge port is the first step. Hey, we have an Apple logo. So good first sign, and we have normal amperage through the ammeter through the charge port. So we should have a normal charging icon when this turns on as well, finally. And that's charging. Green's charging, right? Unplug it. Plug it back in. And we're charging. Finally charging normally. It's at 100% already. This phone is finally turning on. That was, as I already said, catastrophic charging circuit damage. I've never seen 3 different components for the same function get damaged in one single event. Amazing. And by the way, no stolen device protection, so this is going to be a normal and complete extraction. This is 100% successful.